Hi, everyone. Today, I'll be presenting the paper Flamingo, a visual language model for few-shot learning. It is a recent work done at DeepMind. So first things first, why do we care to build this type of models? For multimodal machine learning, we want to build models that can rapidly adapt to various tasks using only a handful of annotated examples. And the most common ways that we've been doing this is to first train the model using a very large data set, and then we fine-tune it for the purpose of specific tasks. But as you all know, this is very data and resource expensive. And alternatively, we have models like CLIP, which can achieve zero-shot learning, but since they are restricted in the set of outcomes, they are not really suitable for more open-ended questions involving specifically like generating languages, like VQA problems. And the intuition for the family of Flamingo models is to treat tasks like captioning or question answering as text prediction conditioned on visual input, instead of solely relying on text input in the more traditional language model settings. And a couple of highlights for the model. And a couple of highlights for the model include that it can bridge powerful pre-trained vision only and language only model. And this is starting from the Chinchilla language model, which is the 70B state-of-the-art language model. And the authors built Flamingo, which is an 80 billion parameters visual language model. Another highlight is that it can handle sequences of arbitrarily interleaved visual and textual data. And moreover, it can handle not only just images, but also videos as input. And the training data is not specifically annotated, and there is no task-specific fine-tuning. The authors also introduced in the paper how they collected some of the interleaved data in the first place, which is just from scraping the web instead of special annotation for machine learning purposes. There are a lot of related works related to the Flamingo model, and here are some of them. So the first one is GPT-3, which was then done in 2020. So GPT-3 suggests that large language model sizes increase performance, and after that, since GPT-3, there has been a lot of really big language models in order to increase its performance. And GPT-3 also popularized the use of in-context learning. And the second type of related work is the multimodal BERT-based approaches. And Flamingo model is different in terms that it does not require fine-tuning on new tasks. And it can also generate text, which is not natively the case for traditional BERT-style models. And third is contrast learning techniques, which is used in the vision part of the Flamingo model. And the fourth is how it compares and contrasts with existing vision language model. So Flamingo models actually share a lot of similarity with the existing VLM models, including like the cross-attention, including leveraging pre-trained models. So we don't have to train everything from scratch. But the difference is that it adapts without fine-tuning instead of having to do a separate set of fine-tuning at the end of training. And it is also versatile in taking in arbitrarily interleaved text, videos, and images. And we'll see how Flamingo accomplished that in a couple of moments. Now, let's talk about the model architecture. So as we can see here, it has two parts, so on the vision side and on the text side. On the vision side, we pre-train a vision encoder with a contrastive text image approach similar to the CLIP model. The vision model extracts semantic spatial features that we would want to query about the visual data, like its color, shape, nature, positions of objects, etc. And on the language side, we start from an existing autoregressive language model trained on large and diverse text. And since Flamingo freezes the weights of a pre-trained visual model and pre-trained text model, it can leverage the large amount of knowledge already stored in the language model weights and the vision model weights. So you can see here in the diagram, the things that are frozen here are marked with this little snowflake and in blue. And the purple parts are the trainable part and the part that makes Flamingo different from other models. So these two parts are one, the perceiver resampler, which can transform visual input into tokens. And this has also temporal features, and the output of this perceiver resampler is a fixed size set of visual tokens that will be passed on to the second part that bridges the vision and language models, which is the cross-attention. And it uses the tokens generating from perceiver resampler to condition the language model. And Flamingo models can model the likelihood of text Y given a sequence of interleaved image and text. So to condition a Flamingo model for a new multimodal task, so we feed it with few-shot prompts by alternating visual inputs and expected text responses. And ultimately, it is followed by a final test image or a video. And once the prompt is provided to the model, we can either sample the output text or evaluate the probability from a fixed set of completions. So this is also related to the training objective of this whole model that we will dive deeper into in a few moments. But the likelihood is really important in achieving the goals of Flamingo. Okay, so now we talk about the first part a Flamingo model that bridges the language and vision part, which is the perceiver resampler. It maps a variable size grid spatial temporal visual features, as you can see here, generated by the vision encoder to a fixed amount of output tokens. So in this case, the latent queries and the fixed number and the output tokens are both 5, but in practice, it's usually 64. And this is beneficial for reducing the computation complexity in cross-attention by reducing it to only a fixed size. And the learned latent queries are the same size as the output, as we can see here, 5 and 5. And vision encoders, so how it works is that it first produces this 2D grid encodings of the images, and they are concatenated together and then flattened into 1D. And this is denoted as XF in this figure. And the keys and values obtained from XF are concatenated with keys and values obtained from the latent query. So in an ablation study later, the authors noted that the concatenation gives a slightly better performance. And for videos, how it works is that the model takes 1 frame per second and encode it independently to obtain a sequence of feature maps. And these are, again, like concatenated before feeding to the downstream components. The temporal encodings are also added to the image encoding, but there isn't really special spatial encoding added because the authors find that the added information actually did not improve the model performance. And that was perhaps due to CNNs already capture such spatial information. And now let's take a quick look back at the overall model. So as we mentioned earlier, there are 2 parts, the 2 purple parts that bridges the 2 models together. And after we generate the visual tokens, they are used to condition the frozen language model via a freshly initialized cross-attention layer between the pre-trained language model layer. So as you can see here, it's like a blue, purple, repetition. And this enables the model to merge visual information for the next token prediction task. Now let's dive into the gated cross-attention dense layers. So these gated cross-attention dense blocks are placed in between the original layers to make sure the visual information are passed on. And these blocks attend the visual inputs with specific cross-attention mask, which we'll elaborate more on the next slide, and as well as a feed-forward part. So for the cross-attention part, keys and values are derived from the vision input, as we can see here, and the query is derived from the text input, as we can see here in the corner. And layer normalization is applied to all attention in the cell of GPT-2. And one thing to note is that it has all these special tangent H gating here. And this alpha parameters is learnable and with initialized to 0. So the reason why we set it initialized to 0 is that the original output is the same as just using a pre-trained frozen model. And the idea is that as the training progresses, it can transition smoothly from a fully pre-trained text-only model to a visual language model. And these layers can also be inserted at different depth frequency. So this is useful for controlling the ratio of fresh parameters over frozen parameters, and also to make sure that we are leverage both the pre-trained model as well as to regulate the model expressivity, memory and time complexity, etc. And here we dive into the masking components that we mentioned earlier. So the authors actually only allow each token to attend to the token of the image that appear right before it. That is the last one before it and in the interleave sequence, as they found it through experiments that the scheme seems to work better than allowing the text token to cross-attend to all the previous images directly. An important advantage of doing this single image cross-attention is that it allows for generalizability, since regardless of how many are used during training, the cross-attention was only done with the previous image. And the authors also show the generalizability by showing that in the training phase, it involves only the 5-shot data, but in evaluation, it can generalize to 32-shot. And putting the previous pieces together, we can now see the full pipeline of Flamingo. So given a text interleave with image video, so for example, something that came from a web page, we first process the text by inserting these image tokens, image tags at the location of the visual data. And then we also begin it with the BOS tag, which is beginning of sentence, and then EOC tag, which is the end of chunk. And the images are processed independently by the vision encoder and as well as the perceiver resampler to get the fixed size tokens that we discussed in the first part. And then each text token only cross-attends. So all of these text tokens, they only cross-attend to the vision tokens corresponding to the last preceding image. And the function phi here illustrates, indicates for each token, like what is the index of the image that it is supposed to cross-attend to. And the dark blue entries mean non-masked and light blue entry means masks. There are different types of training examples, training data sets involved in Flamingo. So one is image text pairs, mostly consisting of a line data set, which has 1.8 billion data points, and L2 data set with 312 million. And the second type is video text pairs, and this contains the VTP dataset with 27 million, as well as the multimodal massive web dub M3W dataset. And from ablation studies later on, the authors also show that if we drop this dataset, the performance greatly decreases. So that means it's really important to have these interleaved dataset in the training process. And these are scraped from web and determining the position of images relative to surrounding text based on relative positions of the text on the original website. Cool. And now we move on to talk about the training objective and model task. So if you recall from earlier, Flamingo can model the likelihood. And here DM and lambda M is the mth data sets, is the mth data set and the positive scalar weighting the influence. So this is like a weighted sum. And the training goal is to minimize this weighted sum of dataset specific negative log likelihood of text. And the authors mentioned that tuning the weight lambda is super important because the different data sets are very different. And in the update step, gradient is computed separately for each of these data sets and then added together, again, using a weighted sum using these lambda coefficients. And the different tasks that Flamingo is used on are one, in context learning with Flamingo models, second, open-ended and closed-ended evaluation, third, zero-shot generalization, and four, retrieval-based in-context example selection. This fourth task is really interesting because when the size of the support set exceeds a certain limit, it is useful if we have a form of prompt selection to both limit the size and as well as potentially improve our prompt quality. And specifically how it's done is that given a query image, we retrieve similar images in the support set by comparing the visual features as extracted from the frozen pre-trained visual encoders. And then we build the prompt by concatenated the top and most similar examples. And since language models are sensitive to the ordering of prompt due to recency bias, Flamingo orders the example so that the most similar support example appears right before the query. And that is how we do like a potential improvement of the prompt quality as well. And here are some evaluation results. Selected here are 3 sets of important evaluation results. On the left, it shows that 6 out of the 16 benchmarks considered, Flamingo outputs fine-tuned state-of-the-art. And notice that this applies to Flamingo with 32 shots, and then even with just previous 0 shots, a few shots state-of-the-art, it only achieves like this gray area, but with Flamingo with 32 shots, which is not many shots, it can achieve or even exceed the state-of-the-art. And in the middle, we see that the influence of shots on performance. So with the exception of star and hateful memes, we actually see that the increase in shots generally leads to better performance. And on the right shows the influence of scale on performance. And again, overall, the more parameters the model has, the better the performance, with the exception of star and BayTag. However, we should also be aware of the competitiveness of each of these benchmarks. But the overall takeaway is that few-shot Flamingo model with only 32 shots in general is often competitive in performance or even exceeds existing fine-tuned methods, which are fine-tuned on many more examples and thousands more, millions more examples. Yeah, those are a quick overview of the Flamingo model. Hope it was helpful, and please let me know if you have any questions.